Okay, good morning, everybody. Make sure this is all working. Uh, we left off right here, went a little bit long on Monday. I'm going to try to make sure and watch the time and not go over. So real quick about the exam. I went through it. The average was 71, high score 100. There will be a curve. I have yet to fully get all of that stuff figured out, so I will. I'll post something with the overall class total with both the first and the second exam curves put into it. It's probably going to be pretty close to the same as the last one. So I'm still waiting to get all of the information from the Proctor Free site, but the scores should show up on Moodle, or should already be on Moodle. I'm assuming you've already taken a peek at that stuff. Any questions, comments, or concerns about that before I start with the lecture? Okay. So I got to give it time. Is the Moodle score including the extra credit with the quiz? So the score you see on Moodle does have the quiz on there, but it's saying that it's out of 10 points, not just extra credit. So you need to take that into account as well. So that is not, it's not part of the overall score, it's extra credit. So however many points you've got, I will tell you again, I'll post on the announcements what the total is for both exams, and then you can see your total score on Moodle and divide it by that number, and that'll tell you where you truly stand. Okay. There also, as far as a few issues, there are tutors that should be available if you go to the content area tutoring program in Rendezvous. I believe it's the 3rd floor. I think the writing lab is up there as well. Not 100%. I know they've moved some things. The content area tutoring should have a tutor that's available. That should be helpful. And yeah, and on my chat, another extra credit quiz before this next exam. Yes, that is true. I'm going to try to get the summary put together and posted, and I will also try to get a quiz up there so you've got ample time to deal with it. It will close before the test opens. Keep that in mind. So there's that. Another thing, I guess while we're still focusing on the exam, another thing that I have noticed, there are some people that it seems like they're moving through the exam relatively quickly, spending 15 minutes or less and receiving pretty poor scores. There are a few that have done it in about 15 minutes and done just fine, but if you're not, really spending the time to thoroughly read the questions and think about it for a minute, that might be part of the issue, is just working through it too quickly. So keep that in mind as well. Okay. I think we're good with all of that. Okay. And hopefully all of the audio and everything is working fine. I'm getting stuff popping up on my screen saying that the internet connection is unstable, but that's all I can do. Okay, so we left off Monday with this image, and UV is a potential for dealing with microbes is really what we're thinking about. It causes the formation of thymine dimers in the DNA strands. So it causes the thymines on the one strand, if they are side by side, they will form bonds together instead of hydrogen bonding with the adjacent strand with the adenine that it should be bonding with. That causes some issues, potentially fatal issues. It kind of depends on the circumstances. It might be a lethal mutation that these microbes experience. With that said, there are some repair mechanisms that try to deal with these thymine dimers to break the bonds in between the thymines and allow for them to properly bond, but it's not 100% effective. There will be one of the labs where we look at a little of this and see the effects of UV light. And it really kind of depends. It depends on the type of microbe. It depends on the exposure of time to the UV light. There's also issues when we think about ourselves, and exposure to, to UV light can cause some issues. And we do have repair mechanisms to deal with this, but it's not 100% effective. It depends on the overall amount of damage. If it was 100% effective, we wouldn't think about issues of skin cancer as an example. I've got a message here from James. Why are the G's paired with the G's and the C's paired with C's? As soon as I read that and I looked at this, I'm like, what the hell? That's an issue. So yes, this right here, I'm assuming you can probably see my arrow as I'm moving it around on here. Guanines and guanines do not pair together, nor do the cytosines and cytosines. I don't know why they're showing that that way. Nice to catch that. Yeah, it should be guanines with cytosines, cytosines with guanines, not that. That is definitely an issue. And this is not the result of the thymine dimers causing this to happen. This is a typo. So nice job catching that. I wasn't even paying attention to that. So this is the problem. This is the problem with the textbook. So you can see here UV light, and we can use that again to sterilize stuff. There are some potentials, laboratory situations where there are some hoods like we're seeing here with multiple lights, just a regular fluorescent bulb or the UV bulb that you could use to sterilize before you've done your project and also potentially after. There are also some of these germicidal lamps that we can use, and we do have one or two of them in the biology building, where maybe there's some issues, where there's some contamination. Bacillus is usually a good one to cause contamination problems. It's a spore former. It's pretty common in the environment. If it gets into a lab, maybe a researcher was working with some bacillus before, and then they're switching it up and working with something else. Well, maybe there's some spores left over that potentially can contaminate. Bringing a germicidal lamp into the lab, turning it on, typically it runs for a few hours, and you are not in the lab when this is happening. The light gets turned on, it's on a timer, it runs for a specific amount of time, and when it's all said and done, it should be effective at decontaminating that lab. At least you hope. If there are still issues with contamination, it kind of might beg the question as far as technique. That could be maybe not so good. Next, irradiation. So gamma irradiation, as we see here, some apples moving through there. This has the potential to sterilize, as well as we think about high energy moving through there. And it's typically we see this where it has some symbol United States. We don't see a whole lot of this, at least not around here. As as I'm shopping at the supermarket, I'm not seeing these things, but there are some potentials for that. again, kind of dependent upon the circumstances. Filtration, there's a couple of different potentials for filtration, and it really, it depends on what it is you're working with. This first image shows some HEPA filters. They remove microbes, they remove all sorts of potentials, endospores, and dependent upon the HEPA filter, viruses as well may be trapped within here. So this is a big filter, and you can see there's all sorts of fiber. If we look at it microscopically, fibers that will trap and slow the movement of organisms as they're passing through this filter. So interception, impact, and diffusion as it's moving through there. There's multiple things, and again, kind of size-wise as far as what might be impacted, and thinking, virus as we get down to this lower size. So these you might see in some of the hoods that are in labs to ensure that what's being worked with, the air gets, it's a negative pressure keeping everything in that hood, but it's got to go somewhere. And as it's removed, blown outside of the building, you don't want to just blow those microbes outside. You want to filter it and ensure that whatever was in there has been trapped. There's other stuff, HEPA filters. You might see some of this in your house. There's different vacuum cleaners that may have HEPA filtration, trapping, it's, allergens, different things like that. Not necessarily thinking microbes, but there's potential for that as well. This is some more filtration, and this, kind of depends on what sorts of stuff you might be dealing with. This first figure, a filter here where you would have, maybe a water sample as an example. The water would be added to the top portion of this. There's a filter right down in here. And as the vacuum is applied, it's going to pull the water through the filter down into this collection chamber below. And what's down here should be sterile. If we are thinking something like water quality testing, the Department of Environmental Quality, there are, other, municipal water supplies are repeatedly testing their waters to ensure that the water they are sending out to the public is safe. Texas, with all of the issues that they've just had last week, is experiencing issues with water, where the water treatment plants were maybe not able to, UV that we showed before is one mechanism where they may be sterilizing the water. Maybe that water was not properly treated, and there were boil orders to ensure that if you were going to drink that water, that it was safe. They recognize that through this process. And as the water is added and moves through the filter, they take those filters and apply them to a Petri dish. It's a small one compared to the ones you've seen in the lab. It's about half the size. And they have a type of medium in there. It's usually it's EMB, the eosine methylene blue. I believe that is the selective media you guys worked with in the lab, but it was a big plate. And as the water moves through there, that filter is flipped over and put onto that EMB plate. It's a very thin filter, and it basically inoculates the EMB agar. As it's incubated, if there are coliforms, in the case of water quality testing, coliforms are things like, your enteric bacteria like E. coli. If they are present, that's an issue, and you definitely don't want to be consuming that. So they show up with that kind of metallic green sheen that indicates coliform organism, indicates lactose fermentation, truly. There are other ideas where we may be, just large volumes of stuff that we want filtered. We're not doing water quality testing, but similar idea. And any of the potential pathogens or microbes, doesn't have to be a pathogen, they would be trapped on this filter. Here's a smaller scale filter where it's attached to a syringe. There are various pore sizes with these filters that kind of like that previous figure on Monday, showing some differences moving through the filtration, where it might be trapping only bacteria, or potentially small enough that maybe we're able to trap more than that, maybe getting to the range of virus as well. Things that can't tolerate an autoclave might be something that we would filter sterilize in this instance. One of the biochemical assays that is performed, and one you'll see in lab in a bit, is a urease test to see if an organism has the enzyme urease and it's got the ability to break down urea. So if that is possible, you get a color change in the broth. Well, urea is very sensitive to temperature. Running it through an autoclave would destroy it, and every test would end up being negative. So the urea is filter sterilized. Same idea as this. The people in the stockroom are using this type of a technique and individually squirting a couple of milliliters of urea into each of the urea broth into each of the test tubes that are sterile to begin with, to ensure that your solution, when you actually inoculate it, gives you an accurate result. So this table gives us an overview of a handful of different potentials that might be utilized, again, for physical control of microbes. So we think about, heat as a common mechanism to try to deal with this. Boiling is a mechanism that is useful if we're not thinking spore-forming microbes. 100 degrees Celsius at sea level, denaturing proteins, altering membrane. We think about cooking, preparing certain laboratory media, personal use, stuff like this. Most of the time we think about boiling. A dry heat oven, 170 degrees Celsius for 2 hours, denaturing proteins, same idea like boiling, but dry instead of moist. Dehydrates, desiccates, things like that. Heat stable devices might be utilized in this mechanism, as well as glassware. It can be dealt with in that dry heat oven. Bottles, glass pipettes might use this as well. Incineration, that's your Bunsen burner, flame in your loop, or the micro incinerator if we're thinking maybe a serious pathogen that you want to prevent it being aerosolized. So exposing that in there, it completely destroys it as it burns it to ash. Autoclaves, this basically pressure cooker, 121 degrees Celsius, typically 15 minutes, or 15 pounds per square inch, so 15 psi, 15 minutes. And at that pressure, we can achieve temperatures much greater than simply boiling. Right? It denatures proteins and alters membranes. All of these have similar sorts of modes of action that way. And sterilizing all sorts of media. Most of the media that we think about from the stockroom that we use in the microbiology labs have been ran through an autoclave to ensure that there is no organism in there. And like I said, spore-forming organisms, it's especially important to ensure that they have been treated this way. Otherwise, once they come back down to room temperature, those spores will germinate and the microbe will grow, and potentially releasing toxins into that substance. Pasteurization, we showed some of this Monday as well. There's a little bit of variation as far as how we may pasteurize things. 72 relatively common, but we may bump it up to a higher temperature, 130 some odd for a second. Denaturing proteins again, and we think about milk, apple juice, honey, and other things that might be pasteurized. All right, not always. There are sometimes apple juice, honey may not be pasteurized either. So you do want to be cautious with some of that stuff. There are other things like, you can see some places where they may sell you raw milk. This raw milk has never been pasteurized. And there are there's maybe good and bad with that. Some feel that the raw milk has more nutrients, more enzymes within there that help to aid in digestion. But there's other issues. I mean, pasteurization ultimately was created to deal with all of the potential microbes in the milk in the first place. It's an issue for sure. I recommend, if you're going to drink milk, and I don't know why you would, but if you're going to drink milk, it should be pasteurized. That's what I say. There are some that maybe will beg to differ and say that raw milk is just fantastic. Anybody want to pipe up and comment on that? Any raw milk drinkers? I have heard a little bit, like maybe issues with a little bit of, low grade lactose intolerance. Things like that might provide a benefit because, again, some enzymes within there that might help with the digestion as well. I don't know, right? And like I said, it's.
Oh, sorry. I was just going to say that my friend's daughter drinks raw goat milk. If she has regular milk, it is explosion.
Okay. So, yeah. And there's, goat milk, cow milk. Yeah. It's, I don't know. I still say, I'm like, yeah, I don't want it. Okay. Yeah, and it's, there are some potentials where maybe it does provide a few benefits. I don't know. As far as the cold for physical control, really we're thinking about inhibition. We're not thinking about killing off organisms. So that sets the stage maybe for some issues. Refrigeration temperatures typically, in the low, maybe 4 degrees Celsius is a common temperature. 0 degree, well, now you're getting close to freezing as we get down, approach that. And sometimes, you might have a spot in the fridge toward the back or something where you want to be careful because things will freeze. There are definitely some potentials with some varying temperatures in there, but usually right around 4 degrees Celsius. It slows or inhibits metabolism, making it so that those microbes aren't replicating rapidly, but they're still alive. And so there are some potential issues with that. There are a few organisms that are what we call sacrophiles. These organisms can tolerate colder temperatures, maybe even some of them thriving in those environments. A few that we think of as far as foodborne illness issues can tolerate refrigerator temperatures. They can grow. They may be replicating slowly, but they're still growing and they're releasing toxins, and it's the consumption of that product that the toxins within that are making you sick. Staphylococcus aureus and Listeria monocytogenes, both of those guys can tolerate the cold temperature. With Listeria, we oftentimes see, you think about putting something in an incubator to try to get it to grow and proliferate. With Listeria, we may hold it at refrigeration temperatures upwards of almost a month, keeping it there to see is it there or not. And Listeria is something that we've maybe heard about as far as foodborne illness and potential recalls. Sometimes you hear about it in ice cream. It's oftentimes like processed lunch meats, things like that, where Listeria might be a common culprit. And they recommend, as far as like lunch meats, hot dogs, things like that, they recommend that you cook them. You definitely should not be feeding, a uncooked hot dog to a little kid because of the potential for Listeria. And, I think back to when I was a little kid, I'm like, I'd open the fridge up, grab a hot dog and just eat it, which now I'm like, that is just disgusting. But there you go. So maybe those were simpler times, right? Eating dirt because it's good for you, right? That's not true. Freezing below -2 Celsius, this stops metabolism. It might kill microbes. It might, all right? But then again, maybe not. And there are definitely, we showed the deep freeze, the ultra cold temperatures that we think about for long-term storage of cultures or medical specimens. There's still the potential for them to be viable when they're brought back to the proper temperature. So not necessarily something that you can think, oh, I popped this in the freezer, I killed all of the microbes that were potentially there, all right? That's an issue, all right? So inhibiting, but not completely annihilating, all right? Pressure, we've got high pressure processing, so kind of coming back up kind of autoclave type of an idea. In this case, denaturing proteins, cell lysis, and we think about this with preservation of food. Hyperbaric therapy, this is something you'd put yourself into. A big hyperbaric chamber, it can slow or inhibit metabolism, and it can also target some of these anaerobic microbes because you're getting a lot of oxygen piped in there as you are in this chamber. So helps to treat with things like gas gangrene. I think it's kind of interesting. This sidebar has really nothing to do with this, but I had back when I was an undergraduate, I knew a guy that he was working at hyperbaric chamber, and he, was like a technician in there. He told me that hyperbaric therapy was an awesome hangover cure. I don't think anybody that's just normally, off the street is going to have access to a hyperbaric chamber to deal with that. He did. And I was just like, wow, that's interesting. But again, it's, providing extra amounts of oxygen, pushing it into your cells, and maybe deep down, that's really what your body needs. I don't know. Kind of odd. All right, desiccation, so drying stuff out. Simple desiccation will inhibit metabolism. Fruits and jerkies could be an example with that. And as we think about this as it's drying, we're removing a lot of the moisture out of it, maybe all of it, and it basically makes whatever product hypertonic. So if there were organisms in there, they're not going to be able to really survive that. Here with this one, or the next one, reduced water, salted meats, fish, honey, jams, and jellies. All of these are examples where we've increased the concentration of, the solutes, again, making it hypertonic, and that causes lysis of those organisms. Lyophilization is a freeze drying technique where freezes under a vacuum. This inhibits metabolism, and when we think about some foods that might be like this, maybe like the freeze-dried ice cream that the astronauts might be consuming, or other foods like that you can get that have been lyophilized. Backpacking stuff, you oftentimes can find some foods that are like this, that are super light, easy to pack. Simply add some water, rehydrate it, and you're back in business. There are sometimes bacteria that we deal with, we order some of these things up, and we typically get them in a lyophilized culture. So it's a freeze-dried little pellet, usually, of bacteria. You take that freeze-dried pellet, you add it back to a resuspension medium, you allow that to stand for a couple of days, and then you take that and add it to a nutrient-rich broth, usually. And then those organisms are revived and you're ready to go, and you produce your stock cultures, and it's basically the organisms you're working with in the lab. Almost all of them have showed up at ISU in a lyophilized form. Kind of interesting. Another side note, there was a professor at ISU, this was a long time ago, maybe 1980s or something like that. There was and I'm assuming it's still there, in the pharmacy department, they had this new machine that would lyophilize things. So this microbiology professor thought, this is awesome, this is great stuff. And he grew up all sorts of different bacteria, and they lyophilized it. They put them into little glass flasks, heated the top of it up and bent it over so it was sealed up. So now you've got this vial that's sealed, and inside of it was all of this powder that was the lyophilized bacteria, all right, all sorts of stuff. So there was a box that was in one of the labs that contained all of these lyophilized bottles of bacteria. And after, so 2001, after 9/11, there were all sorts of issues. There were thoughts of, just bioterrorism, more than just terrorism, but bioterrorism. And there were all sorts of things that, people in the lab needed to go through and inventory and say, oh, I have these substances or I don't. There were microbes that we at one time worked with that we no longer could because of some potential issues. Something that we commonly grew up and showed in the laboratory situation, but there's potential issues with that. And we don't really mess around with that bacterium anymore, even though it's relatively common. So again, I'm kind of going off on this, but we find this box that this professor he made all of these things, all sorts of little vials, and they have labeled right on them what they were. Some of them were just normal things that we still worked with, and others where you were like, oh, we're not supposed to have that. Every single one of those, it was kind of a sad situation. Every one of those vials got broken open. They got added to broth. They basically started to grow. And as soon as they were inoculated and incubated, they were taken out of that, put into the autoclave and killed and destroyed. And I was like, that poor guy, he made these things and we've had, they were viable. They would be viable indefinitely. But we couldn't keep that stuff around. So we dealt with it by destroying it. And it was kind of odd. Will we need to memorize this table for the exam? No, you do not. So we're just going on. I mean, you'd want to think there's different mechanisms. So heating, cooling, pressure, desiccation, and radiation, but all of the details with that, you don't need to know that stuff. It's just different potentials. All right. So yeah, the lyophilization, freeze drying. Radiation, we were just kind of looking at a little of this in the previous slide. Ionizing, X-ray or gamma ray, thinking about that, sterilizing things, maybe spices and other stuff, food products could be dealt with. In Europe, more common, right? US, not so much, because the idea with that, you say radiation and the first thought is, oh, I'm going to eat this apple, I'm going to get cancer. And that's not the case. But that's kind of the issue with that. The non-ionizing, this is like UV light, again, creating those dimers that causes mutation. So kind of a interesting bit with that. So this last little bit to the table, sonication uses sound waves, ultrasonic sound waves, causes cavitation, so empty spaces, disrupting cells, causing the lysis. We do have some sonicators in the biology building. Usually with that, it's something that's happening in a hood. And you also, as you're in there, you have ear protection on because it will destroy your hearing, even though you don't know it is because you can't hear it. You have to wear hearing protection. You're in that lab, the door is closed, and usually there is a sign on the outside of the door saying sonication in use. So somebody doesn't just open the door and walk in there because they wouldn't have ear protection on. That's kind of crazy. The HEPA and the membrane filter, we saw that right before we started these tables. So again, with air or with liquid for those filtration techniques. So this last bit of this chapter is talking about all sorts of different types of compounds. There's a lot of different molecules that I'm going to show you. You don't need to get bogged down with this stuff either. Just let me go through it. It's all fine and good, right? Phenols and phenolic compounds. definitely been used to control microbial growth. It's also, phenol is also known as carbolic acid. That's this first bit right here. So you got this big aromatic ring and then some potential side chains attached to it, maybe a double ring. So there are all sorts of potentials with this, bactericidal and fungicidal properties with this. There are, you get a sore throat, you spray is it chloroseptic? I think that's the throat spray. It's got a phenol compound within there, and it helps to numb the area in your throat, but it also helps to kill some of those organisms. Well, you swish that around or let it sit at the back of the throat for a little bit, and then you spit it out. You are not supposed to swallow that stuff down. A little bit's probably not that big of a deal, but that's the idea, right? And some of you've maybe used a little of that, know what I'm talking about. I have another story for you, and it's all about phenol. Phenol, I told you, numbs the skin, or the back of your throat. It is something that is hazardous. This story goes back, it could be back to the 1980s as well. It was in the biology building. This was back when the hospital was right across the street from the biology building. That's maybe a bonus. There was a researcher who had a jug full of phenol. Typically, when you are working or carrying materials that are hazardous, you have them in secondary containment. So you've got your jug of phenol, and it is in a plastic container with a lid that is sealed tight on there. So if it were to drop and break, the phenol stays contained inside of the plastic container. That's what we think of as common practice today. He's carrying this jar of phenol down the hallway, and something happens. It slipped out of his hand. It hit the floor and shattered, broke. Phenol all over the floor. He slipped and fell in the phenol and basically kind of bathed himself in phenol. As he lands in the phenol, like I said, it numbs your skin, but it does a little more than that. You don't realize it, but it is burning the skin. You don't feel it because your skin is numbed. So he's getting severe burns as he's trying to get up and out of the phenol. He falls back into it and basically kind of covers himself in phenol and received severe burns all over his body. After that point, and you will recognize in the biology building on every hallway, there are safety showers. In most of the labs, you can see eye wash stations and a safety shower that is very near. A lot of the research labs, there are safety showers in those labs as well. And the reason for that is this phenol. And the biology building was built in the early 1970s. The safety showers were retrofitted in after the fact because that was not something that was thought of beforehand, but it's there now. And it's for things like this. If you happen to get chemicals like phenol on your body, you need to rinse it immediately. And at that point, modesty goes out the window. You strip your clothes off and you shower, or you potentially die because you didn't. Crazy. So yeah, carrying things around like that, you want to make sure that you've got secondary containment, and you really ought to know what you're working with in the first place and that it does pose serious hazards. This image, I think it's a little outdated. Triclosan is something that, as far as I know, has been banned, at least in the United States, a couple of years back, maybe 2017. I can't remember exactly. Something that was pretty common. It was found in soaps. It was found in all sorts of things. They had triclosan that they were putting into clothing products to make it antimicrobial, different clothing, like, maybe shirts or something that you're, gonna athletic wear that you're gonna wear as you're working out, that might get a little stinky. Well, not if it's got triclosan impregnated into it. That kills all of those organisms. Now it doesn't smell. Well, I think you still ought to wash it, right? So there are definitely issues with this. And there's environmental and health risks. There's resistance that we've definitely seen with some microbes to this, causing problems. I recall triclosan, seeing it in, I want to say, in toothpaste. It's, again, not something that we see, at least in the United States anymore, because it has been banned due to the, serious impacts. And as we see the hand washing, as we talk about all of these things and we think antimicrobial things, you see antibacterial soaps where they've got different things, not triclosan, impregnated into them. Deep down, soap is your best mechanism, not putting antibacterial substances into it. Just simple soap. Washing properly will help to remove those organisms. Washing your hands with antibacterial products is like, just taking antibiotics just for the fun of it. Do you think that's really a wise idea? I think not. So you want to keep that in mind if you are purchasing soap. You ought to be. Okay. As far as metals go, there's all sorts of potentials with this. Oftentimes, we think of them being antimicrobial. So here we've got a copper door handle. Copper has antimicrobial properties, and microbes, as from your hand as you touch it, it ultimately does not allow them to proliferate on the surface of that door handle. So making it a little antimicrobial. All right. If you touch the handle right after someone touched it, the potential for, this is a fomite, the potential to pick something up from that is definitely there. But if it's just sat for a little bit of time, typically it would not allow that organism to persist. There's, in a laboratory situation, stainless steel equipment, bench tops, things like that might be inhibitory. Here we've got some silverware that actually have silver in them that help to inhibit. Inside of incubators, sometimes maybe stainless steel, but it also might be some copper lining like the door handle to inhibit that. Mouthwashes, the antiseptic mouthwashes with some zinc chloride, also inhibitory. There's potential for some alcohol in there as well that you're going to see as antimicrobial, but the zinc is an example. And this poor dude over here, argyra is a condition where it's a bioaccumulation, it's irreversible. So taking like colloidal silver can accumulate within him, and he's basically turned blue. His skin, the whites of his eyes are now silvery, and yeah, like we said, it's irreversible. So you want to use caution with that. Here we've got betadine, an iodine solution, and putting it onto the skin before some sort of incision or surgery, something like that. It's a topical antiseptic. And there are, definitely, if you go into donate blood or something like that, usually it's maybe just an alcohol swab. But if you are going into the hospital and you're going to, have an IV, you're, there for, it's likely that they've treated that with betadine beforehand. At least I believe that's the case, not just for, in this case, maybe a spinal tap's going to happen. I don't know what's happening there. So here we've got different ammonia products, monochloramine, one of the chloramines derived from ammonia that ultimately antimicrobial, and it's basically, replace the hydrogen with the chlorine on there. Here we got a couple of alcohols, hand sanitizer, ethyl alcohol, so grain alcohol, if you will, something you could think of as consuming, but you shouldn't be consuming hand sanitizer because there's other stuff in there. And then the isopropyl, third carbon on there. You definitely don't want to try to consume this stuff. This is rubbing alcohol, so either of which have disinfecting properties with that. And with the pandemic that we are in, I think everybody is very familiar with Purell, right? Is there such thing as too much Purell? I prefer just washing my hands with soap and water. But I will tell you the foaming hand sanitizer that has been in the labs and up on my podium, that stuff, I don't know what the deal is with it, but I think it is fantastic. A little squirt of that. It's got maybe a little bit of lotion or something in there. It's good. The other alcohol ones, I have heard they have switched them. Last semester, I thought it smelled like the cheapest tequila you would ever smell. I don't think you'd ever even want to drink that. Terrible. They've switched them out with some other bottles, and I guess it doesn't quite smell that bad, but I don't know. Some of you might be like that. Well, that smells delicious. Maybe that's a problem. Okay, here we've got some soaps. So with this, there's these big hydrocarbon tails, and with that, they're going to get in and interact with the oils, thinking like on your skin, and they're going to help to break that up and kind of collect that and rinse it away. So they also can get in to the phospholipid bilayers of cells and cause damage. That's moving away from that to a couple of quats, benzalkonium chloride and acetylpyrimidine chloride, kind of similar, big hydrocarbon tails. Here we've got a plasma membrane, and as they get in, the blue dots are the specific quats. They get in and cause permeability issues within the membrane, basically disrupting the integrity of the membrane, causing those cells to lyse is really the idea with that. Looks like I've got a chat. Madeline Leslie says, is there a study group I can join? And I know in the chat Monday, Cassie Alvarado, maybe. I don't have the same chat up, and I don't know if Cassie is tuned in today. She said she was starting a study group, and I'll look back on that. I will see if I can find that, and I will try to post that on the announcements as well. Are you there, Cassie? Not hearing her. So there's potential with that. There are also, again, the content area tutoring, the CAP program and Rendezvous might have an individualized tutor for you. I know I had a message from them that they were trying to find somebody, and I think they've got that in place. Does anybody know that? Has anybody sought a tutor yet? Okay. Well, with that, I will stop. I'm going to stop on time today. Stop the sharing right here. Okay. Any other comments or concerns before I end it for all? Okay. I hope you all have a great day. We'll wrap up this Friday and start chapter 14. And again, I'll look through that and find details about that.